All right, so this is lecture number 25 of the Wireless Communications Lab. And today we're going to continue talking about MIMO communication. In particular, we're going to do two things. First is we're going to look at detection in spatial multiplexing systems. So we're going to derive the maximum likelihood detector and then talk about the zero forcing receiver. So you should be able to derive both of these receivers here. And then the second topic, hopefully we'll have time to finish, is performance analysis of spatial multiplexing. And here we're going to derive a bound on the probability of vector symbol error for a spatial multiplexing system with a maximum likelihood receiver. And the point of this will be to show that spatial multiplexing, even with the best receiver, doesn't get potentially all the diversity there is in the system. And we'll also get some insight into what errors look like in a spatial multiplexing system. So first, just a quick review of what is spatial multiplexing here. Remember that the basic idea was we were going to introduce this new block in the system that takes symbols on the input here and splits them up across different transmit antennas. And so, for example, if this was a spatial multiplexer with two transmit antennas, then the spatial multiplexer would send, let's say, the even antenna symbols on the first antenna and the odd symbols on the second antenna. And the thing to note is that we end up sending two symbols at once. And the other point to recall is that after the RF up conversion, etc., there was in this case, with two antennas, square root of Vx over 2, square root of Vx over 2. So there's also a total power normalization. So we're going to send two symbols at once, but we're not going to send twice the power. We're actually going to send, in this case, with two transmit antennas, half the power. If we had four antennas, we'd send a fourth of the power. And I say power because, so this is a square root here, and remember that, the energy was would be Ex over 2, power would be Ex over 2 times t, the symbol period, and then the sum power across all the antennas would be the sum of that, which would be square root of Ex, or would be Ex over t. So that's the spatial multiplexing idea. So now let's look at detection for a spatial multiplexing system here. So what we're going to do first is we're going to derive this block diagram for spatial multiplexing. I think we did this, part of this in the class last time, and then we're going to look at the received signal structure. So this is going to be the detection. That's what we're going to focus on here. But we're going to start off here by looking at a narrowband system here. So we're going to focus on flat fading. And we're going to consider a system where so what I'm going to do is, instead of using this ideas of like even and odd, I'm just going to use a subscript here to denote the symbols riding on a particular antenna. And just make the notation easier here. So we'll consider a system that looks, roughly like this here. Of course, I'm not drawing out the match filtering, the upsampling, the pulse shaping, all of that stuff here. We have multiple transmit antennas, NT. We also have multiple receive antennas, specifically NR of them. And there's a channel between every transmit and receive antenna, which we call H of K, comma L. And so the K is the receive antenna index, and the L is the transmit antenna index here. And what we want to do here is we want to write an equation that corresponds to the observation at each receive antenna here. And so let's look at the kth receive antenna. Let's call it y sub k of n. And then, under this flat fading assumption, using this power normalization, square root of ex over nt, this received signal here sees a linear combination of the transmitted symbols times the channel times the normalization, which I'm putting here. So this is going to see ex over nt, and then we're going to write this like h. So remember, this is receive comma transmit. So this is going to be, we're looking at the kth receive, transmit antenna 1, that's S1 of n, plus h of k comma 2, S2 of n, plus dot dot dot, plus hk comma nt, s of nt of n here. And then we also have to remember that there's still going to be additive Gaussian noise, and we'll call that vk of n here. So a main difference between the scalar case and the spatial multiplexing case here, so if we had just a single transmit receive antenna, there would just be one symbol, one channel coefficient, one noise term. Now we have still one noise term, but we have a whole bunch of channels, and we actually have a mixture between, these are the different channel coefficients here, and then these are the different symbols. And so the tricky part with spatial multiplexing here is that each receiver sees a linear combination of all of the transmitted symbols here. Now the idea that what we're hoping to make this work is that if each receiver sees a slightly different linear combination, then maybe we'll have enough differences in the observations to put the original signal back together. So that's kind of intuitively the idea. Now, to formalize this, we're going to find that it makes a lot of sense because we have essentially here, this is an equation in the unknowns S1 through S of nt. We're going to find it useful to write this in terms of a linear system using vector and matrix form. So what we're going to do is we're going to stack the, take these observations here, and we're going to stack them into an equation here. So I'm going to put like y1 of n, y2 of n, all the way down to y of nr here. I'm going to write this whole thing out here, this nice vector form here. So first of all, the easy one here is the vk of n. So this is just going to be v1 of n, v2 of n, dot, 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 vnr of n. And then this over here is s1 of n, s2 of n through s of nt of n here. And then now we just need to fill in the appropriate rows of this matrix here. So we start by looking at this with k equals 1. This is h1 comma 1, h1 comma 2, dot, 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 h1 comma nt. Continuing, h2 comma 1, h2 comma 2, dot, 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 h2 comma nt, all the way down to h of nr comma 1, dot, 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 h of nr comma nt here. So all we've done is we've just taken the channel coefficients and stacked them here into rows. And we've done this because every receive antenna sees the same observation of the transmitted symbols with the different linear combinations, different set of weights, and different noise here. And we're going to rewrite this here using this vector form. Call this y of n is equal to h. H will be our channel matrix times vector s of n plus v of n here. And this is, oh sorry, I forgot the square root of ex over nt, which we're going to use for performance analysis. So this whole thing here is the kind of canonical MIMO input-output equation here. So there's multiple inputs, which are the symbols here, multiple outputs, which are the y's. And this H matrix here is an NR by NT matrix. So most every paper you see on MIMO has some variation of this equation here, sometimes without the power normalization. But most papers that have flat fading have more or less this equation here. Okay, so that's the spatial multiplexing system model here. Now, let's look at a couple things here. So let's talk about the power and the dimensionality here. So y of n is an nr by 1 vector. S of n is a nt by 1 vector. V of n is nr by 1. And H is nr by nt matrix. That's our system of equations there. And then for transmit power normalization purposes, what we're going to do is we're going to assume that, so let me just write that down here explicitly. The way that I have written the equation assumes a particular normalization that corresponds to what we've been assuming in class. So we're going to assume that each symbol sk of n here has been normalized to have unit energy. This is just like the assumptions that we always make. Now, in some places you'll see that the symbol energy is normalized to be 1 over nt. And that's why I have the factor of nt on the outside, as we'll see here in a moment here. And the second thing that we're going to assume is that we're going to assume that the transmit symbols are also uncorrelated here, so that their average value here is 0. And then based on these two assumptions here, and also you have to remember that the constellation is 0 mean. So I didn't mention that here, but that's always the case here. Now, if we look at the expectation of the symbol vector here, S of n, S star of n, which corresponds to the covariance matrix because it's 0 mean, then the off-diagonal terms are 0, the on-diagonal terms are 1, so this is just an identity matrix here. And then the transmit power, how we define the power here essentially is going to be the trace of the expectation of S of n, S star of n. So the trace is just summing the diagonal. It's an operation that sums the diagonal. And that's just equal to nt here. So effectively, in a MIMO system here, so we're kind of summing up the transmit symbol energy here. We see that we have, uncorrelated symbols. Each symbol is normalized to 1, so that effectively there's nt worth of energy here. And therefore, if we consider our transmitted symbols to be square root of ex over nt times S of n, then the normalization becomes ex power here, because you get essentially ex over nt times identity, which leads to the trace of identity times ex over nt, which is equal to ex here. So these assumptions here, effectively, because we've assumed the symbols to be unit energy, that's basically why we need this factor of nt here. So that's why I went through this kind of pain to explain that here. Any question on that normalization? Okay, so now what we want to do is we want to derive a detector that takes the observation y of n and finds the best guess of the vector s of n that was sent. And so we're going to use the maximum likelihood criterion just like we used in the beginning, earlier lectures in the course. So this is maximum likelihood detection. So first of all here, we have to talk about what constellation is used to create each set of symbols here. So to make this problem easy, we're going to assume that every symbol sent on antenna K comes from the same constellation C here. But you can actually allow generalizations where you have different symbol constellations for different antennas. Now that only makes sense when you have some feedback, and since we probably won't get to that in the course, we won't discuss that. Now, what we're interested in the maximum likelihood detector problem is actually we have a vector input-output relationship here. So, in fact, what we're going to do is we're going to try to find a likelihood function for y of n given a particular vector value of s. And so we actually care about the set of possible constellation points that this vector constellation takes. So the vector constellation is actually what is important here. So if we assume this right here, then we look at the vector s1 through s of nt. What we see is that this vector here, it lives in some sort of a higher dimensional constellation space, because each of these, you can have each constellation point here, and here, and here, and here, and so on here. And we write this as, essentially it's like a Cartesian product of all of these different constellations, which you can kind of write like this here. And the important point is that the cardinality of this, the number of possible constellation symbols, is the size of your constellation raised to the nt power here. Right? And to see that here, consider like if we had BPSK, so suppose a constellation is -1 and 1, and we had nt equals 2, we'd have 4 possible sets of symbols. 1, -1, 1, 1, -1, 1, -1, -1. So in this case here, our vector constellation is, these 4 points, and the detector would have to pick one of these 4 points based on the observation to see, which was the best one here. Now, if I had nt equals 3, I'd have 2 times 2 times 2, so I'd have 8 possible vector values, and so on here. And you can see that the larger the constellation, and the larger the number of antennas, the bigger this set is. So the set here easily can be very large. And that's kind of the whole point, because the whole point of spatial multiplexing is to send a lot of information at once. So this is the set of possible vector symbol values here. So now what we're going to do is we're just going to take kind of the same approach that we took before. We're going to suppose that, that we take a specific value of s of n here. Let's call it, call it s hat of n is in this constellation here. And we're going to look at the likelihood of y of n given s hat of n and h here. So we're also going to assume that we know the channel here perfectly. And now we're going to derive the likelihood function here. Well, going back to this equation here in red, if you know h and you know s, You don't know v. V is complex Gaussian, random vector. And if you know this here, this is a constant. So the resulting y conditional distribution is complex Gaussian with mean square root of ex over nt h s of n, and then the covariance will actually be the covariance of the identity here. So it would be identity times n naught here. I should write that down over here. Yeah, I'll write that on the next page here. So we note that the distribution of v of n is complex normal, zero mean, and identity covariance here. And we've already dealt with this distribution a few times. We did this when we derived the probability of error for the maximum ratio combiner. So we saw the distribution function before. All we have to do now is plug in with a slightly different set of parameters here, which is what we're going to do here. So we're going to take the distribution function here. So I'm going to write this as f of y given h comma s. I'm going to plug in y of n here, given some value of s of n here. So let's suppose that s of n is equal to s bar. We have h here. And then we're calling that complex normal distribution, multivariate distribution. This distribution function looks something like 1 over pi to the nr. Determinant of this covariance matrix RV, e to the minus y of n minus square root of ex over nt h s bar star covariance matrix inverse y of n minus square root of ex over nt h s bar here. So here all I've done here is I've used the fact that v of n is complex normal, zero mean, and covariance RV, which is equal to n naught times identity here. So that's all I've done here. Now, essentially, what we want to do here, so first of all, let's use the fact that RV equals n naught times identity. Then this is equal to 1 over pi to the nr. Determinant, you have to dig up some old linear algebra results here. Determinant of an identity matrix is the product of the diagonal entries. So it's going to be n naught to the nr. And then over here, we have the inverse of a diagonal matrix, which is just a diagonal matrix of the inverse of the diagonal entries. And that's also n naught. So we can actually rewrite this as e to the minus n naught inverse times y of n minus square root of ex over nt h s bar star y of n minus square root of ex over nt h s bar here. Okay, so now what we're going to do is we're going to do the same exact simplification steps that we did before here. You know, you shouldn't be afraid that there's vector entries here. So now we're going to say that, okay, so the maximum likelihood detection problem is to find the s hat of n, which is equal to the arg max, where I'm going to look for all s bar in this vector constellation of this f of y given h comma s, y of n given and then using the same logic that we used before, we're trying to maximize the function of, so we have these two things here, right? We have this constant here, and we have the exponential. So I'm trying to find the maximizer of this function here. That doesn't change multiplication by a positive number here. So that's equal to the argmax of S in this constellation here, e to the minus n naught y bar of n minus square root of ex over nt h s bar star y of n minus square root of ex over nt h s here. And then the same logic that we used before here, that maximizing some exponential function is equivalent to maximizing the argument of the exponential function, but the argument here is negative. So this is equivalent to minimizing the argument of the negative function here. So this is arg min s in this vector constellation set here of this quantity here, which is n naught, y of n minus square root of ex over nt, h bar, s bar, star, y of n minus square root of ex over nt, h bar, s bar here. So we're going to minimize this quantity here. Now the same logic before, we can get rid of the n naught here. And then further, look right here. This is a vector times its conjugate transpose, which is just the norm squared of this vector. So for ease of writing, I can rewrite this as the norm of y of n minus square root of ex over nt h times s squared. And so this is actually the detection rule here. Okay, so essentially, just to summarize here, we're going to go through here. We're going to implement, so the ML detector implements this S hat of n is equal to the arg min S bar in this big S here, norm of y of n minus h s bar squared here. So note that the complexity here is actually high. If you implement this directly here, like for example, you'd have to multiply this h times this vector s here, compute the difference, square the values, sum them all up here. Now you can do some smarter things. You can pre-compute h times s bar, and that saves some complexity. But still, the other problem is you have the size of this set of vector constellations here. So you have essentially many operations done c to the nt times. Now, in practice, for the most part, you wouldn't actually implement this directly. You'd implement one of a whole family of lower complexity techniques that generally are either maximum likelihood or usually near maximum likelihood. For example, you might use something called a sphere decoder, or a lattice, lattice reduction technique, lattice-aided receiver. I forget the exact acronym, but that's something like lattice-aided receiver. It's probably not right. But the idea is that there's some structure in this space of S here, and you can use that structure to partially search through the space very efficiently. And so these are alternatives here, which we won't talk about in class. But I did want to mention that we wouldn't necessarily implement this here directly. So that's the ML detector. So any questions on that, the detector here? Yes?
The complexity is because now the constellation size is increased.
Well, it's two things. It's that, you now have, before we had an absolute value squared here. So now you've got, if you pre-compute this, you've still got NR absolute value squareds now. And you have to do this C to the NT times. So that's sort of where the complexity comes from.
In actual practice, how many antennas are generally used?
Well, you might use, in most systems right now, it's up to 4 typically. So 4 transmit and receive. That would be for a better implementation in 802.11ac. Cellular would, the mobile, you often have 2 receive antennas. So you could have 4 at the transmitter. You don't do, yeah, I'll get into the dimensionality in a minute here, but typically 2 to 4 transmit antennas and 2 to 4 receive. And if you have a lot of extra transmit antennas, there's other things that you might do. And so I'll explain that a little bit in a minute here. So other questions? Okay, because of this high complexity, we want to find, an alternative receiver structure. And so an alternative receiver is a linear receiver. So the linear receiver is a general class of receivers that operate something like this here. They take the y of n into some block here. They apply to this y of n some matrix here. Let's call it W. And then the output of that you detect independently. And then the output of this here would be your S hat of n here. So effectively with the linear receiver, we're going to find a matrix that we're going to use to multiply onto y, and then we're going to detect each observation of that independently there. And then this matrix, for this whole thing to make sense, would have to be some kind of an NT by NR matrix. Because you have to go from the number of receive antennas back to the number of transmit antennas. So there's different ways to do this. I mean, the approach that we're going to take is just the simplest one, which is called the zero forcing receiver. And with zero forcing here, effectively what we're going to do is we're going to find the, so we're going to consider, the same system that we had before here. Y of n equals square root of ex over nt, h, s of n, plus v of n. And we're going to try to find, some sort of an inverse of this matrix H here. So first of all, we're going to suppose that the number of receive antennas is greater than or equal to the number of transmit antennas, so that our channel is either square or tall. And further, we're going to suppose that it's invertible, or at least it's full rank, let's say. Then we can solve this problem. Let's suppose that we solve like y of n is equal to square root of ex over nt, h, s of n using least squares. Well, if we were solving this using the least squares, neglecting the noise, we know that we would, the final solution would be s of n is equal to, right, we'd multiply through by this, and then multiply through by its inverse here. So we'd have this effectively square root of ex over, actually I'm going to, I'm just going to leave the square root of ex over here just for convenience here. So we multiply through here by h, and so we get h star h inverse h star y of n. And this quantity here is known as the pseudo-inverse of H. And this is what we're going to use for W. So then what we're going to do is we're going to then form this new value Z of n, which will be equal to Wy of n, which is equal to H star H inverse H star Y of n. And then this is going to be equal to square root of Ex over Nt S of n plus H star H inverse H star V of n here. Now, it turns out that, so effectively what we've done here is, this looks a little bit like remember the Alamuti equation that we had? We did all these tricks, and we ended up with the desired symbols here, plus some noise. And with the Alamuti equation, what we did is we went through and we showed that the noise covariance was also amazingly an identity matrix because of some special orthogonality property. Here, that's not the case. So the suboptimality of the zero forcing receiver comes because this right here ends up being correlated noise, except in very special cases. And what that means is that the noise sample at one point is related to the noise sample on another one here. Now, by doing the detection independently, we are neglecting that correlation. And so that's actually where the suboptimality of the zero forcing receiver comes in. People think it's because of the inverse, and that's not really the inverse. It's really the fact that we don't pay attention to the correlated noise here. So that's essentially the zero forcing receiver here. So then what we'll do is we will just to be like totally clear here. So we're going to take this output here. So this would be, let's say, step 1 here. And step 2, we'll take the kth entry of this right here, and we'll pass it into a detector. And so we'll say that S hat of k of n is equal to the argmin of S in C, the constellation, times absolute value of zk of n minus square root of Ex over nts, absolute value squared. And we do this for k equals 1 through nt. So here we have nt searches over cardinality C here. With the maximum likelihood detector, we had C to the power of the number of symbols to the power of nt, and then we had nt computations for each search there. So you can see that we've reduced the complexity, substantially. Now, indeed, we do have to compute the pseudo-inverse here. But, if you're processing like 100 symbols, you only need to compute the inverse once. So that gets amortized over the fact you're using it again and again and again. And so then, just to summarize here, we get, so with the zero forcing solution versus the ML, you have something like NT times modulus of C operations here, whereas here you've got something like C to the NT. And then further, there's that NT as well. And so essentially, the issue comes in, it's just that exponent there. So now, it'll turn out that we won't have time to do all of these derivations here. You have to take my other class, space-time wireless communications, to see all of the details here, but that the error performance of maximum likelihood is actually much better. So better probability of symbol error. And then this one here is worse here. So sort of a trade-off here. You get the best detection performance using maximum likelihood, but you pay in terms of complexity. Now, it turns out that when you combine the zero forcing receiver with other features of the system, coding, adaptive modulation, that the end gap between these two isn't necessarily that big. But, you know, it is true that this one, in some sense, should be better than this one. And in fact, there's other reasons, like if you have what's called a soft decoder, this turns out to be much harder than this. So there's other kind of practical trade-offs to be made that we won't discuss here. All right, so that's the spatial multiplexing receiver here. So should be able to, you know, derive that detector and then derive the zero forcing receiver there. So any final questions on those two? Yes. It comes from terminology used in equalizers, actually quite old, because effectively, yeah, let's see here, zero forcing. Yeah, it's like if you have a filter and you try to find the direct inverse solution of it there, the let's see, yeah, the zeros actually blow up on you here. I don't know. I'm not actually sure why it's called zero forcing here. Just kind of an old equalization term. Yeah, you could, yeah. Now, it turns out that in the case of maximum likelihood, in the scalar case, they're the same. So you can divide by the channel and perform the detection, and it's the same as doing the maximum likelihood. And here, if we divide out that channel and then we perform detection independently, we will lose optimality here. Now, if you were to do maximum likelihood detection on this, if you were to do maximum likelihood detection on this vector here, it would actually have the same performance, but it wouldn't simplify, because you'd end up with a noise covariance you'd end up with the noise covariance here that doesn't simplify. So kind of it's just kind of like factoring an inverse out here and sticking it in there. So the real thing is the independent detection there. So other questions? Let's take one break here for a second here, using my favorite RCR Wireless website. It's my go-to place for finding news about wireless, especially when preparing for class here. This is just an interesting article about the interest in fitting small cells with Wi-Fi. So small cell is like a very small portable, not necessarily portable, but a very small base station that you could use at your house. Small cell could also be used in buildings and on lampposts. So in the reason that small cells are interesting is that if you have a lot of cells, people can connect more often to like a strongest base station, and there's more cells so that more people can be served a larger fraction of the time in a given cell. And there's interest though now in also kind of in parallel offloading. So offloading is like instead of connecting to the base station, you connect to Wi-Fi. There's different advantages and disadvantages. One of the issues with Wi-Fi is that there's a lot of congestion in the Wi-Fi spectrum. And then there's also, you have to be able to seamlessly kind of hand off to Wi-Fi without actually having to enter some, acknowledgement, acceptance, and so on here. But the spectrum is unlicensed and it is free. So the carrier is effectively taking people on their expensive licensed spectrum and shifting them over to some other free spectrum. And the only thing it costs is having that Wi-Fi access point here. So there's a lot of discussion now about combining these small cells and kind of Wi-Fi together so that the small cell could actually also offload to Wi-Fi itself. You wouldn't have to have like a separate Wi-Fi access point. And I don't know, I find this interesting, I guess, personally, because I find my phone's Wi-Fi turning on all the time. My phone seems to associate with Wi-Fi quite a bit, and half the time it doesn't log on, and it's really annoying. And I can tell because I'm like surfing the web, and then it stops working. And then I realize that the Wi-Fi has, it offloaded to Wi-Fi. I don't know. Does anyone have that experience here? I mean, even when my Wi-Fi is off, the phone turns it on and associates with my carrier's Wi-Fi, which half the time is not working. Well, I want to say too many bad things about my phone here. I don't think it's the phone. It's probably the carrier that is not implementing the Wi-Fi very efficiently. That's a good question. Yes, excellent question. Yeah. I don't know. It could be something to do with my setting here. Yeah, I don't want to, speak ill of my, phone carrier here, but I do find it sort of annoying here. But there's some interesting theory associated with it. So it's like I understand why it's trying to do it, but I actually don't understand when I explicitly turn the Wi-Fi off because I don't want it to do it, that it turns it back on for me. Yeah. Well, I mean, I don't know. So your phone doesn't do it. Interesting. Yeah, it might not be Verizon that I'm using. Okay, that's good to know. Anyone else have this issue here? Anyone else even notice it? It happens all the time on the UT campus. We get offloaded all the time here because they don't have a lot of base station towers. I mean, we have distributed antenna network, but the capacity is not really high enough to support all you students surfing the web all the time during professors' boring classes. So you get offloaded either to the restricted or you get offloaded to one of the other brands. Okay, well, there's no way to find something as exciting as the wireless cockroach, so I don't know what to say. All right, yes?
It's like offloading from a licensed bank to an unlicensed bank.
Yeah. Yeah, that's the term. So offloading is used for licensed to unlicensed, whereas otherwise it would just be like handoff. Yeah. Yeah, it's technically a very interesting problem, this whole issues of offloading and capacity with small cells and with offloading and with congestion. So it's not an easy question for us to answer in terms of analysis or for the operator to configure in real time. Because, they'd have to have some knowledge of how loaded the spectrum was, especially the unlicensed spectrum, and have some knowledge of how, if they bring someone in, how it affects the loading. And, yeah, it's interesting problems. All right, so, next thing we're going to do today is performance analysis of spatial multiplexing. Theory, we should be able to do this in the time we have remaining here. Basically, we're going to derive a bound on the probability of symbol error, and we're only going to do this for the maximum likelihood receiver. It's possible to do it for the zero forcing receiver. Mathematically, it's a little bit more complicated, but it is possible. I did some analysis of that many years ago, so it's not too hard. So, error probability here. So what we're going to do is we're going to derive a bound on what I call the vector symbol error probability. Because we are detecting a vector, to me it makes sense that we look at the probability that we mistake one vector for another here. So we're not going to look at the probability that one particular symbol is decoded incorrectly. Rather, we're talking about the entire vector. So a vector error can have two symbols in error, not just one. So we're going to look at effectively here. So I'm going to introduce some notation, but it's relatively simple what we had before here. So probability of Ex over N naught given H. It's going to be a function of, S and R again. We're given the channel. And effectively what we want to compute is the probability that, and I'm going to use here these superscripts to avoid confusion with the subscripts here. We send some vector S of k in our constellation, but unfortunately we make a mistake and we decode as some S of L of n, k not equal to L here. So that's the probability of vector symbol error, and we went through similar arguments last time about why this was hard to compute, even in the scalar case, and then we computed some upper bounds. And what we ended up with was our favorite here, union upper bound. And that's what we're going to use here too. So remember, in the union upper bound, we had the number of points in the constellation minus 1. Here, it's c to the nt minus 1. And then we were going to look at the worst case error. And so what we need to do is we need to find the probability of vector error over all possible pairs of vectors such that the probability of S of k to S of L is maximized here. And this is the pairwise error probability. I wrote this in like a slightly different form when we did the error bound for the QAM type constellations here, but effectively it was the same thing there. We ended up looking at the worst case possible error, and we found that the worst error occurred for the two symbols that were closest together, and those were separated by the minimum distance of the constellation, or dmin. Here we're going to have actually a somewhat similar result here. So let's look at, first of all, what does this probability here look like? Well, without going into kind of the detailed derivation here, basically for an ML detector, so let's see here. So supposing we have a maximum likelihood detector, we're going to detect argument of S in this constellation here, such that y minus square root of Ex over nt h s is as small as possible here. Now if we're looking at the pairwise error probability, our constellation only has two vectors in it, S of k and S of L. And so an error occurs when S of k is sent, coded as S of L. And so what that means is that y minus square root of Ex over nt h S of k, even though that's what we sent, that distance is actually bigger than y minus square root of Ex over nt h S of L here. This is just what happens when there's an error here. Now, kind of for similar reasons, as we argued in the scalar case here, and without going through this detailed calculation here, you only make an error here effectively when well, yeah, all right, it's a bit complicated to explain that here, but let me just give you the main equation here. So this pairwise error probability is equal to Q of the square root of, we have the same thing as before, Ex over N naught. And here's kind of the new piece that I'm struggling to explain without explaining a lot more. Effectively, we need to look at the distance between these two constellation points, just like we did in the scalar case. Here, this is the Euclidean distance between h s of k, that vector, and this other vector, h s of L, squared over 2. So this is effectively, if I have like some complicated space here, and this is h s of k, and this is h s of L, half of this distance corresponds to this quantity right here. So this takes the place of kind of like the minimum distance between two constellation points. It's half the distance between two vector constellations. And you can show, and we do not have to show that for this class, that this is the appropriate generalization of exactly the same concept in the scalar case. In the scalar case, these were just, in these two complex points, and that distance between them would correspond to the minimum distance. Now, the other thing to notice here about this equation here is that I've been very careful to leave the h inside here, because it turns out that the distance between two vectors changes if you multiply each of those vectors by another matrix. So what's actually important here is the product between h and that vector s of k, and the product between h and the other vector s of L. So that's another one of the differences here. So essentially, the pairwise error probability, it generalizes to the vector case, and then its generalization looks like this here, where this is the minimum distance over 2 here. Okay, so now, given that here, what we want to do is we want to derive a bound here on the minimum distance here. We want to derive, bound on the probability of error. So first of all, I'm going to just stop for a second here and point out that if we were talking about just an additive white Gaussian noise channel, so suppose we're looking at the additive white Gaussian noise channel here. So not looking at the average probability of error, but just the probability of error given the channel here. Then we would try to maximize this quantity here over sk and s of L, q of square root of Vx over n naught times h s of k minus h s of L squared over 2. Maximizing the q function is equivalent to maximizing the argument of the q function. So this is square root of ex over n naught. Sorry, that's equivalent to minimizing the argument of the q function. Min s of k, s of L, k not equal to L here. So if we're trying to get an upper bound for the additive white Gaussian noise channel, the worst case is where these two vectors happen to be close together here. Now, the tricky thing here is that, again, we have this h here. So what happens is, let's say, like on each of your antennas here, you send 4 QAM. You send another 4 QAM over here. Well, what you have at the receiver is some higher dimensional, so this is like, 4-dimensional, 2-dimensional complex. It's hard to illustrate here. But basically, you have 1, 2, 3, 4, 1, 2, 3, 4. So 4 times 4 is 16 possible points here. So here in this 2-dimensional complex space, which I'm not going to illustrate very well, effectively you have 16 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points here. And these points are all different possible combinations of these constellations times your matrix channel here. And so what you'd have to do to find this minimum distance here is you'd have to enumerate, in a very basic way, you enumerate all possible products of h times these different vectors here, and then find the ones that are closest together. Say, for example, these two here. And so then this would give me that minimum distance here. So in the probability of error case here, then the performance would be determined by these 2 points here. Now, so the weird thing is that the channel is changing over time. So somehow our performance depends on this minimum distance, and yet that's really determined by the channel. It's not determined by our constellation. So that's just kind of one of the weird properties here of the maximum likelihood detector. But that's one of the reasons that makes it interesting. It's also one of the reasons that that feedback is very important, because you could imagine if you knew that these two constellation points here were really close together, if you knew this h at the transmitter, you would do something to the transmitted signal so that these points either were excluded or were somehow pushed further apart. And that you could use generalizations of transmit beamforming to do that. And again, we won't discuss that in the class, but you can see that if you take 381S with me in the spring semester here. Now, so that's for the AWGN channel, and I will start talking about the derivation for the average probability of error, which now I'm realizing that we won't have time probably to finish here, but I think it's worthwhile to start here. So let's look at the expected value of h, expected value with respect to h, of the probability of error given the channel here. And that's less than or equal to s minus 1 min of, again, the s of k, s of l here, expected value of h, of q, the square root of ex over n naught, s of k, oh shoot, I forgot the h minus h s of l squared over 2 here. And the new feature is we're going to take the expectation now. To do this, we need to describe somehow the distribution of h. So let's consider what is commonly called the rich scattering assumption. So with rich scattering, what effectively this means is just that there's enough scattering so that the channel between every transmit and receive antenna sees a whole bunch of different multipaths, and therefore the values add up differently, and so we can treat them as being effectively independent. And in particular with rich scattering, we assume there's lots of paths, and so every channel coefficient tends to be Gaussian, let's say 0 mean and unit variance, and because they're assumed to be independent, the expected value between h of k, l, and h of m, n is equal to delta of m minus k, delta of n minus l, which is equal to 0 if m is not equal to k and n is not equal to l here. So in the rich scattering assumption, the channel is just basically it's just Rayleigh for every transmit receive antenna pair, and it's independent between all of them here. So that's pretty much it here. Okay, so with that assumption, now Now, that's also the same assumption we made for analyzing the performance with maximum ratio combining and with the Alamuti scheme. The only difference here is that we've now generalized it to multiple transmit and multiple receive antennas. Now, the other kind of tricky new piece of information we need here is that we have a matrix channel now. Before we started with a scalar, then we went to a vector, now we have a matrix. Usually, when you talk about matrices and you talk about matrix random variables, the calculus ends up being easier if instead of talking about the distribution of the matrix, we talk about the distribution of some function of the matrix. In particular, what we will use is the distribution of this operation called the Sveck here. This you may not have seen before. So what the Sveck operation does is it just takes the columns of the matrix and stacks them into a vector here. So for example here, if I had a vector here of a matrix with columns H1 and H2 and H3, and I was to apply this vector operation, I would end up with one really long vector with entries H1, H2, and H3 here. So we then say that this matrix channel H has distribution, complex multivariate distribution with zero mean and with covariance matrix of dimension of an identity, but of dimension NT-NR by NT-NR. Because if I vec this H together, you can see here that if this is NR, 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 I have NT, NT, NT. So I have NT times NR coefficients here. So that's essentially the property that we're going to use here. Now, the second property that we're also going to use, so let me call this here, it's going to be 1, and then I'll basically stop with this next property here, is that we need to use a fact that if I have 3 matrices and I multiply them together, and then I stack the columns of of that product, you can rewrite that using something here. You can rewrite that using C Kronecker product B times the vector product of this A here. So this is a Kronecker product here. So we'll need this fact here to simplify some of the expressions, because we're going to end up stacking up a product of vectors, and we're going to have to rewrite that product in a form that looks something like this here. So we'll see what this is in the lecture on Wednesday, and then how to use it to evaluate the average probability of error. So just to review here, so we looked at the performance analysis of spatial multiplexing here and derived a bound on the probability of vector symbol error rate for the Gaussian channel. And then we were in the process of deriving that same bound for a fading channel. And so we'll finish that derivation on Wednesday. And some of the reasons I like to do the derivations is there's some sort of interesting mathematical tricks that get involved in there that, it's just kind of fun. After that, we're going to talk about channel estimation with spatial multiplexing systems, and then we probably won't finish all that on Wednesday, but then we'll continue into synchronization and OFDM, and then that'll pretty much be the last lecture, and we'll have a review. So that's where everything is going here. I think that's it today here. Let's see. So to summarize here, so we derived the detector for spatial multiplexing. You should be able to derive the ML detector, derive the zero forcing receiver here. So I could imagine giving a related problem on, let's say, the final exam here related to one of these. And then we also started talking about performance analysis here. Here we're not going through a lot of details here, but I want you to get out some of the intuition, like in the additive white Gaussian noise case, the intuition is that the constellation is distorted by the channel, and what we care about is the distorted constellation. So that's like the first point here. And then we'll see something else surprising come up in the performance in the average channel here. All right, that is it here. There should be homework assignment posted, but it's not due until the last week, which would be the week after next. And then I also will drop the lowest homework assignment, but I strongly discourage you from not doing the last assignment, because I will have some coverage of that on the final exam. And so if you don't do the last homework assignment, then most likely you won't study the material very seriously, and then you'll miss those problems. And that'll probably mean the difference between a higher grade and a lower grade. So I encourage you to work on that homework and, drop one of your earlier ones if possible. All right, thank you.